You should start slowly because then more people will be coming.
Сегодняшняя лекция, которая является предварительной для завтрашней.
Let's make noise.
You know, Lüroth has a bell she rings in order to get the people to the seminar.
But I'm doing that.
Ah, yes.
Actually, more loud than.
You think so? The spell was impressive. So, okay. So, first of all, thank you very much for having me here. Also, if there are questions, please ask immediately. If I'm too fast, if I'm too slow, please tell me. So, today, I will talk about unirationality. Supersingularity. And the formal Brauer group. So, I will introduce all these notions on the way. And let me start with, what's the most clever way? Yeah. So let me start with unirationality. Now, we say that a variety, so what's the easiest algebraic variety there is? Some people might argue that's projective space itself. So what would be the next easy variety? That are those that are dominated by projective space. So definition is X is called, let's say, of dimension. Algebraic varieties over some field. In most cases it will be an algebraically closed field, but at the moment it's not so important. Say of dimension. And we will say it's unirational. Unirational. If there exists a dominant and rational map from P to the n onto X, which by definition, X is also n-dimensional, so this map is generically finite. I'm not assuming that this actually is a map, so it's only defined on an open-dense subset. If we are in characteristic 0, then by Hironaka's theorem, then we know that we can resolve the indeterminacy. So after some blow-up, we really get a morphism. As far as I don't know, we still don't know this in characteristic P. So, but nevertheless, we can define unirational like that, or equivalently. So this is a geometric notion. I can look at the function field of X, and this map will induce an inclusion into a purely transcendental extension such that this will be a finite index. Conversely, if you have such an inclusion, then there exists an open-dense subset such that this inclusion gives rise to a finite morphism, closing up sort of from between some open set inside F and N space, mapping dominantly onto an open set here, and so extending, we get a dominant rational map. So this is really equivalent. This is a question in geometry, so this is something which looks more algebraic. And so there is a small variant. In case the characteristic is positive, so the characteristic and this inclusion here, so this is a finite field extension if this is separable, so no multiple roots, and then X is called separable. Unirational. So, what are the consequences? So, of course, the easiest example of a unirational variety is projective space itself, or affine space, but let's stick to proper varieties. So, in view of what I will be talking about tomorrow as well as next week, let me draw a couple of consequences. So, if X is proper, for example, projective over K, and unirational, we see that simply choosing something like that, we have a family of lines in here. And this gives rise to an infinite, sort of a moving family. So non-constant maps from P1. Because we have many maps from P1 here, so it's just lines. They move a lot. So of course this is only defined on an open-ended subset, but sort of because this is so this gives you only a priori a rational map, but this is a curve, so it extends by properness. So we get non-constant maps from P1 to X. So we get infinitely many rational curves on a unirational variety. And so a rational curve by definition is an integral curve on my variety with normalization as P1. So this is one consequence. And the second consequence, which is maybe which only works if X is smooth. So I have a smooth and proper variety, and I know, suppose it's sort of, I can look at the sheaf of Cantor differentials, and to make it interesting, I can take its ith exterior power, and even to make it more interesting, I can look also at tensor products of this sheaf with itself, and then can look at the global sections of these things. So these are finite dimensional K-vector spaces, and what I want to say is that in the separable unirational case, or in the unirational case in characteristic 0, all these numbers have to vanish. So, first fact. If X is projective space itself, then we know then these numbers are 0. For all, so for example, let's take the most known case. If I is equal to big N, then this is the canonical sheaf, which is O of minus N minus 1. Clearly this has no global sections. And if I twist this K times with itself for some number, it's even getting more negative, still no global sections. So what I want to say is that for projective space, all these numbers I produce this way, at least if I and k, I mean if k is positive, there's 0. And now we do a sample computation, namely, which is less trivial than one might think if one thinks a little bit longer about this. So these numbers are sort of birational invariants. So if x is birational, to Pn, and still smooth, because otherwise this sheaf doesn't really behave nicely, then still all these vector spaces are 0. So why is this interesting? Because now if x is separably unirational, so we have a map like this, such that the field extension here is separable. I want to argue that in this case also these numbers have to be 0. Why is that? Because suppose for a moment, I mean, you don't really need this. Suppose we had resolution of indeterminacy. Characteristic, this is okay, but you can avoid this argument. Then you can sort of, there exists some blow-up. These global sections still will, sort of these vector spaces will still be 0. And then we have a morphism, which is generically finite. So suppose you had a global pluricanonical form, then you could simply pull it back. If it was non-zero before, it would survive the pullback and it would still be non-zero, which it cannot be, because here all these numbers are 0. Okay? Because however, there is something interesting going on. If the characteristic is positive, and x is inseparably unirational, then let me do the following very simply, sort of, do the following example. You can look at the map that sends t goes to d to the p, and you can look at the pullback of the form dt. So this is a typical example. This is a 1 form. And so if you pull that back, what you get is d to the tp, which is nothing but p tp minus 1 t, which is 0. So this sample computation shows you that if you have an inseparable map, if you have an inseparable morphism in characteristic p, and you pull back a section, sort of here in this case, a 1 form, then even though this 1 form was non-zero before, after pullback it becomes 0. So what this tells us, that this line of sort of this observation here, namely that if you have a unirational variety, or even more generally, a unirational, let's say unirational variety, that these numbers have to be 0. This kind of argument doesn't work anymore. And in fact, Zariski was, I think, the first in the 1950s, 1960s to give examples of surfaces of unirational surfaces. For curves, it cannot happen for a different reason. For unirational surfaces where these numbers are non-zero. In fact, he even gave examples of unirational surfaces of general type. So let me kind of, this is kind of the starting observation, that unirational has some interesting applications if the characteristic is 0. X. I have now a smooth, projective, or smooth and proper variety over a field. I take the canonical sheaf. Which is the top, so this scalar differentials wedged to the dimension of X. And I define the nth plurigenus to be the dimension, it's a finite dimensional vector space. Yes. So my questions, this invariant is known, not known? Known?
Who knows this invariant?
So the question is how much I have to explain about this.
Well, about half.
Okay, I say
More than half knows.
Okay. Well, this is not a democratic decision. I was just curious. So the thing is, as I said, I mean, as you know, I mean, you want to extract, I mean, ultimately we want to classify varieties, right? And somehow we want to have easy and computable invariants. And actually, if you think about it, the canonical sheaf is the only thing that gives you something. And so these numbers is something you get for free if you start with a variety. You know, you start with something smooth and proper. You need some assumption. You need smoothness because otherwise this sheaf behaves badly. And if you don't assume properness or projectivity, this won't be a finite dimensional vector space in general. So you get these numbers. So associated to every smooth projective variety or smooth and proper, I get this bunch of numbers. And what I want to say is that because these are too many numbers, you look how they grow. So you have the Kodaira dimension. Which is sort of, it's usually denoted by kappa of x, which is defined to be minus infinity if all these numbers are 0. It is defined to be 0 if these numbers are bounded and not all 0, and it's said to be Kodaira dimension D if Pn grows approximately like d to the n if n goes to infinity. Now you have to prove something, and this is called by Riemann-Roch. So this is a remark or an exercise. First of all,
Maybe add to this.
oh yeah, thanks. You're perfectly right. Thanks. So by Riemann-Roch, this is well defined. That is, given a smooth and proper variety, it really sort of this number, these PNs really have one of these growing behaviors. And moreover, it lies in the range of, it lies in between, so it's minus infinity, 1, 0, and so forth, and it can grow as much, sort of can grow at most like n to the dimension of x. And so, exercise. Well, actually, it's a straight point. So we have that the Kodaira dimension of projective space is minus infinity, because I just told you that if you start with projective space, then these omega to the I kth tensor product with itself. So this is just a special case of the observation that all these vector spaces are 0. It also shows that if the characteristic is 0 and x is unirational, or if the characteristic is positive and x is separately unirational, then I told you that these vector spaces coming from pluricanonical forms are all 0. So also in this case we have Kodara dimension minus infinity. So this is a very kind of rough sort of extra number that you get for every variety. It's a birational invariant, by the way. And so let me see. And proper curve. Well, you probably agree that this is not an interesting invariant for points. So let's see what it is for curves. Then we have the following. Then we have the genus of x, which is nothing but in this new terminology P1 of x. This is the genus. And so this should be known, that the genus is 0 if and only if the curve is P1. But it also shows that all the plurigenera are 0. And this says that the only curve of Kodara dimension 0, of Kodara dimension minus infinity is P1. X elliptic is equivalent to the genus being 1. It's equivalent, that's a straightforward exercise, to all the higher plurigenera being 1. Because omega x is trivial, so also higher tensor products with itself will be trivial, and we only get one global section. So this tells us that we get Kodara dimension 0. Genus bigger or equal to 2. I wrote this down. So this grows like n. In fact, it's something like 2n times g minus 1. So this is just Riemann-Roch. So this tells you that, like, in terms of the Kodara dimension, the curves are divided into P1, elliptic curves, and curves of genus bigger or equal to 2, which is a reasonable classification. And so let me rephrase this for a curve. The following are equivalent. X is P1. X is unirational. So this means that Kx function here sits of finite index inside some purely inseparable, purely transcendental field extension. And the Kodara dimension is minus infinity. This is actually also true in positive characteristics. So a curve is separably unirational if and only if it is unirational. The reason being that the only inseparable morphism there is in characteristic P is the Frobenius, and so everything can be factored by that, and the Frobenius doesn't change the type of the curve. Questions?
The equivalence between the first and second in the curve is called the Lüroth theorem.
Yes, thank you. Thank you. So this is the Lüroth theorem, and then there is the Lüroth problem, which asks, do we have an analog of this in higher dimensions? Is it true that every unirational surface is in fact rational? And so let me just state the following theorem. Actually, can you read it if I write here? Because I don't know whether the computer obstructs the view.
I think
It's okay. Yeah, you can up. You can see, I told you. And so, let me mention the following theorem, which is due to Castelnuovo, which says that X be a smooth and projective surface. So I should say if the characteristic is positive, this is due to Zariski. Then the following are equivalent. Namely, X is rational. That is, i.e., birational to P2, i.e., the function field of X is just a purely transcendental extension in two variables. And secondly, now this is an interesting result. He says that we can characterize rational varieties in terms of cohomology groups. So he says that H1 of X should be 0, so the first cohomology of the structure sheet. And the second thing is he says that the second plurigenus has to be 0. I should say, of course, the original conjecture before Castelnuovo was that in fact H1OX should be 0 and P1 should be 0, because these would be kind of the easiest invariants. But then some of you may have heard of Godot surfaces or of Enriquez surfaces. These are examples of surfaces where H1OX is 0, P1 is 0, so these general, the arithmetic genus and the geometric genus are 0, and which are not rational surfaces. In fact, that was the original motivation to construct. And the third thing, it's equivalent to saying X is separately unirational. So let me comment. A couple of implications are trivial, some others are harder. So if X is rational, that these numbers vanish is very easy to show, because it suffices to compute them for P2, where it's an easy exercise, and then you have to show that these numbers are birational invariant. So this is easy. Also, well, if something is rational, then clearly it's separably unirational. So this is easy. And also, if a variety is separably unirational, by the remarks I made earlier on, it's not difficult to see that these numbers are 0. So this is easy. So why the name Castelnuovo and Zariski is there is really because 2 implies 1. That if you have these numbers vanishing, that this implies that X is rational. And as far as I know, we do not have a characterization of rational varieties in higher dimensions, right? In terms of cohomology. No. So, non-trivial. In particular, we see that this Lüroth theory has an analog in dimension 2. So the Lüroth problem, whether this holds true in higher dimensions, is true in characteristic 0 for surfaces. It's false in characteristic P if we do not insist on the separability. And it's also false in dimension 3, even over the complex numbers. And so, let me also say that, what do I have here? Actually, what's my time? Do we have a... Okay, so, Let me, I'm not sure some of you may know this. Let me also mention a guiding principle. Namely, this is here. We have the following conjecture. If X is smooth and projected over the complex numbers, and it is of Kodaira dimension minus infinity, then what do we believe? Then, this is the conjecture, there exists a Y of dimension 1 less, and a dominant rational map from Y cross P1 onto X. So the dense image. Clearly, if a variety has this property, this is called Uniroot, then of course the Kodaira dimension will be minus infinity by the arguments I've given you. If you have a pluricanonical form here, you can pull it back, and if it was non-zero here, it would be non-zero here, and you get a contradiction. But as far as I know, this is okay if the dimension is free. That's the last thing I've heard. And it seems to be related to the abundance conjecture. So all I want to say now is we have this invariant, the Kodaira dimension. We know that Kodaira dimension minus infinity, the case when all these plurigenera vanish, for curves is equivalent to saying it's P1. For surfaces, it turns out it's equivalent to being birational to P1 cross a curve. Or it also turns out we have this nice theorem by Castelnuovo which tells us something is unirational if and only if it is rational. So this belongs to the same thing. And we have this conjectural picture here. So the questions is, can we find invariants? That detect unirationality. For curves, genus. For surfaces, rationality can be detected computing these two numbers. Can we do this? And somehow, a related question is I may come back to this next week. If a variety contains many rational curves, so integral curves, whose normalization is P1, and there is like infinitely many of them, or moving families. Is it in some sense unirational or uniroot? Uniroot is this. So I should say because I will address this next week, let me mention a conjecture in this, because I'm in his office, I have to mention him today. We have the following interesting conjecture, for example, Liedtke Unirationality, who says that, we do know what's going on for curves, so let's look at surfaces. So if X is a K-free surface, that means that the first cohomology group of the structure sheaf is 0. The dualizing sheaf is trivial. For example, a smooth quartic surface in P3 would be an example. In particular, this means that P1 of X, so Pn of X is 1 for all n, and it's surely not rational. Then X contains infinitely many rational curves. So this is something I just want to mention, because the easiest way of producing rational curves, images of P1, would be that there is some P2 sitting above the rational about a given surface, and then we just take images of lines. This cannot be the case here. Nevertheless, there is this conjecture that there are infinitely many rational curves there, which cannot be related to unirationality. And if true, the interesting question is, where do these rational curves come from? So up to now, this is still part of the introduction. I want you to kind of see that the objects I'm interested in is rationality, unirationality, whether something is dominated by projective space, whether there's many rational curves, and what we can say. Are there implications? Are there easy implications? Are there more difficult ones? And so in order to detect unirationality on surfaces, it's interesting to introduce the following invariant, namely the formal Brauer proof. So that would be section 2. So maybe I should say, are there any questions up to here? Okay, everything is clear. So suppose I have a variety which is proper over a field, for example, some projective variety, and then I want to define, well, actually not I, Artin and Mesa did that. They considered the following thing, namely, they considered a functor that they called phi upper I, or phi upper n, x, which goes from local Artinian K algebras with residue field K to abelian groups So how does it go? I associate to such a local Artinian K algebra, well, it doesn't look very natural at the first sight. I'll explain to you why it is natural. We take the trivial product family, x cross s. So we take the product with this kind of, think of this local Artinian algebra as something like a fatting point. Then we take elements in O star. And then we have a map from this cohomology group simply by restriction to Hn(x) all x star. So I take the cohomology class here and I restrict it to the special fiber, and I want this to be 0. So I look at this. They studied this functor, and let me maybe I call it deformation cohomology, because you think about this as deforming cohomology classes. And so the question, what is it? Well, for n equals 0, we don't get anything interesting. It's just K star goes, that's not very interesting. For n equals 1, we get the first interesting thing. Because H1 of x with OX, with values in OX star, that's just pig, right? That's just the set of invertible sheaves. Now, what is this? This is the set of invertible sheaves on this trivial product family, which become, so I have an invertible sheaf here, line bundle on this space, which becomes trivial when restricted to the special fiber. So what is this? Phi 1 of x, of some of these s, is nothing but an s-valued point of p. With sort of, right. So this is just a map from S to P naught, such that the special, sort of the closed point 0. So in particular, if I plug in S equals K epsilon, so epsilon squared, what do I get? I simply get the Zariski tangent space to pick. Oh. Then, now, if I take something which is larger, what do I get? I get kind of infinitesimal neighborhoods. I get all the infinitesimal neighborhoods around this point corresponding to OX of pick. And so in the language of formal schemes, and this is just, I mean, we won't need this, but I mean, I want to have it on the blackboard once. So what we get so this is the formal completion of pick x at the 0 section. So this is something which carries definitely more information than the Zariski tangent space, but nevertheless the information captured by this phi 1 is entirely something infinitesimal. So if it just was for phi 1, then Artin and Mesa would not have studied that, because we have the Picard scheme, right? So why would we bother about phi 1? The interesting thing is you can look at these things for higher n, and then something interesting happens. Namely, so n is equal to 2, then hx over x star is called the Brauer group. So I have to ask against the, who has seen that before? Is this familiar? Okay. So this is the Brauer group, and as with the Picard group, which classifies invertible sheaves, the point is with the Picard group is that there is a Picard scheme, right? Those points parameterize line bundles. Unfortunately, there is nothing like a Brauer scheme. And I think one can even show by examples that even if X is a very reasonable variety, there is nothing like a Brauer scheme because there are simply too many classes that cannot be points of some variety.
There's something we call germ scheme, or spaces, spacer germs.
Yes, yes. If you, I mean, but since I don't want to talk about Atsumaya algebras here, yeah, there is something, but in this sense, we can look at phi 2, which is deformations of these Brauer classes, and this is called the formal Brauer group. which doesn't need any fancy techniques or gerbs or so forth. You can, you know. And what Artin and Maser were interested in, they wanted to know, for example, whether this group is, whether this is represented by something. And so, question. Oh no, that's just a proposition. They have a more general result, but that will be okay for what I will do. If X is proper over K, so for those of you who have seen deformation theory, it will not be very surprising that there is a deformation obstruction theory for these things. And so the automorphisms of phi1 are classified by H1XOX. The tangent space to this functor is H2XOX, and there is an obstruction space which is H3HOX. So if we have this, and if H1OX is 0, no automorphisms, and H3 is 0, no obstructions, then this here is nicely pro-representable. Pro-representable by a formal group law. So, I have to say a couple of words about formal group laws. So again, I have to ask who has seen formal group laws before. Sort of, I'm kind of interested just to see where the audience is. Okay, this is less people than before, I think. So what is a formal group law? I'm only interested in the one-dimensional case. I will sketch what it is, and also I'm only interested in the commutative case. So one-dimensional commutative formal group law is a power series, say over K.
They're supposed to know categories very well.
Ah! Oh, okay, great. So it's a group object in the category of formal schemes. Now I can proceed, right? Of smooth formal schemes, I should say. Because that's the smoothness which is also important here for the initial. So it's just sort of, let me boil this just down. You can write this as a formal power series in two variables, which has the properties that it's of the form x plus y plus higher order terms. It's associative. And finally, it's commutative. And so I should say, how do you think of these objects? You think of these, so y. You take the formal spectrum of a power series ring in one variable, and you want to turn it, so this is a smooth formal group, a smooth formal scheme. You want to turn it into a group. So to turn it into a group, I have to give you a multiplication map, among other things, which boils down to giving a map from the formal power series ring in one variable to this product here, which of course, because we're in the category of formal schemes, this is a completed tensor product, so this is nothing but a formal power series ring in two variables. This element t has to go to some. It's completely determined by knowing where t goes. So I get some formal power series, and then it turns out that the group axioms, namely associativity, for example, becomes this, commutativity becomes this, boils down to saying that a group object, turning this object into a group, is equivalent to giving me such a formal power series in two variables, having these properties. so let's say. And of course, if you want to have a higher dimensional thing, it's just what you would get if you take the formal spectrum of k t1 comma to tn.
May I ask a question?
Yes.
Do you mean that this formal Brauer group is one-dimensional?
This is not in this sort of, no. The dimension of the formal Brauer group in general will be H2OX.
Yeah.
But in my applications later on, I will be only interested in one-dimensional formal group laws. You're perfectly right. In general, you get it. It's commutative, that's clear. But it will generally, the dimension will be H2OX. Because H2 is actually the tangent space to that functor. Sort of in my application, because one-dimensional formal group laws is something we can actually classify. So that looks, I mean, so I'm only interested in the one-dimensional case here. And so let me give examples. The easiest thing, of course, to write down would be x plus y. So this is called the formal additive group law. Then you can write down x plus y plus x times y. This is the formal multiplicative group law. And then there are these people in number theory who study Lübli-Tate formal groups who know how to write down much more complicated formal group laws. For me, for the moment, these two will be sufficient. And so we have the following facts. When studying formal group laws over a field, in case the characteristic is 0 and G is one-dimensional and commutative, then it follows that there exists a unique strict isomorphism. I don't need that at the moment. So what is only important? It's isomorphic to GA. There is only one formal one-dimensional group law in dimension 1. If it's commutative, if it's n-dimensional and commutative, there exists a unique strict isomorphism to GA to the n. So this map, not surprisingly, is called the formal logarithm. And so how do you construct such a formal logarithm? For example, if you want to write down a formal logarithm from GM to GA, well, as the name suggests, you write down something like sum minus 1 to the n, x to the n divided by n. But you also see what the problem is if you do this in characteristic p. At the moment when p divides, your denominator, you're in trouble. Therefore, in characteristic, so this kind of power series approach. I mean, the nice thing about these formal group laws is really, you do usually induction with power series, and that works pretty well in characteristic 0. But if your characteristic is positive, it's no longer true that they're all mutually isomorphic. There is an extra invariant coming up. So G one-dimensional and commutative. And so what can we do? So it's given, say given. Well, if it's in characteristic P, it's natural to look at multiplication by P. So there exists a map P from G to G, which is multiplication by P. So formally, this is just by F of P. You think of adding x plus y is something like f comma x plus x comma y. So x plus x, 2 times x should be f of x comma x. 3 times x should therefore be f of x comma f of x. Well, you know what I mean, right? So I abbreviate that by this. And again, it's given by some formal power series. Then either multiplication by p is completely 0, or it's something, I mean, of course you have to show something, which looks like t to the p to the h plus higher order terms. And h is called the height. In this case, we simply set the height to be infinity. Now, I leave it to you that, so, exercise. Well, you see it here already, right? Here, multiplication by n is really multiplication by n in the classical sense, right? F of x comma x really is 2 times x. So multiplication by p in this case really is p times x. We are in characteristic p, therefore we are in this case, multiplication by p is 0. And so the height of the formal additive group law is infinite. Now, this here is a little bit messier. I want to do this on blackboard. I mean, you see, let's do the characteristic 2 case, right? That's easy to see. F of x comma x would be x plus x, this is 0, plus x squared. So it starts with x to the 2 to the 1. So the height of the formal multiplicative group law is 1. And this tells you already that there cannot exist such an isomorphism from here to there. So the reason that we cannot write down a logarithm is not that we have to do it somewhere else, somehow else. There is no logarithm map. So we have this. Interestingly, I'm not sure, I think this is due to Lazare. We have the following, so G1, G2, one-dimensional, commutative. Actually, you can show that over a field, every one-dimensional formal group law is automatically commutative, but that's not trivial. Group law. Then, first of all, they're isomorphic. If and only if they have the same heights. So the height is the only invariant. And secondly, for every h 0, 1, 2, up to infinity, there exists a formal group law. There exists. So you see 2 cases here, and I think I've been told recently that the people doing Lüroth theory can write down the other cases quite explicitly. Okay. So, how much time do I have? Half an hour, right. So we have this interesting invariant now, associated to an algebraic variety, with these assumptions on the vanishing of cohomology. We have this formal group associated. And now I want to explain how this is related to questions about unirationality. And somehow, my main interest, I mean, if you don't know where to start, you know, we have something which we understand for curves, so let's do surfaces. And if there's something we don't understand about surfaces, let's look at K-free surfaces first. And so, smooth projective surface. Again, question to the audience, who knows that? Your students, of course, but yeah, I mean, you should. So, I mean, there is something like, for those, I mean, why is this, I mean, why are people interested in that? we introduced the Kodaira dimension earlier on. If a surface has Kodaira dimension, sort of there's this Enriquez classification, Kodaira Enriquez. Maybe I should bring the name Shafarevich here as well. Otherwise they won't let me go. So if there is this classification of surfaces, Kodaira dimension minus infinity, so it's birational to P1 cross a curve. Kodaira dimension 0, interestingly, there are 4 classes. It's birational to either an abelian variety of dimension 2 or a quotient thereof. These are the hyperelliptic ones. And then there is this other class called K3 and the quotients of that, which is Enriquez. So kind of the building blocks in Kodaira dimension 0 are abelian surfaces, abelian varieties of dimension 2, and these K3 surfaces. And so examples are, for example, smooth hypersurfaces in P3 of P3-4, so vortex, or Kummer surfaces. And so we have that H1OX is 0, because that's part of the definition. We have H3OX is 0, because it's a surface. And we have that H2OX, so the dimension of the second cohomology group by cell duality. This is nothing but H0 of omega x. This is one-dimensional. And this tells me that this functor we studied before, the formal Brauer group, and that is why I was interested in one-dimensional group laws, is a formal group law of dimension 1. And if the characteristic of K is positive, we can look at the height of the formal Brauer group, which gives me a new invariant for a K3 surface in characteristic P. Actually, for those who know about moduli spaces, so there is a 19-dimensional parameter space for polarized K3 surfaces, and the height gives rise to an interesting stratification of this moduli space. So the generic K3 surface has height of the formal Brauer group equal to 1. So there is an open dense subset of surfaces inside this 19-dimensional space having this property. There's a divisor inside this moduli space where surfaces have height at least 2. And then there is inside this, there is a codimension 2 locus where the height is at least 3. And it goes down to, well, maybe I should say, well, what are the possible values?
Is it related to the rank of the car group?
It is. But maybe, yes, let me postpone this question for a second. Theorem X, a K3 surface. It is, but in a very weird way. K3 surface in characteristic P. We have H, the height of the formal Brauer group, and we have rho, the rank of the Néron-Severi group. So we take the line bundles, the Picard group, which is a finitely generated abelian group for a K3 surface. I mean, modulo linear equivalence, but this doesn't matter for a K3 because Pic naught is trivial. So this is a finitely generated abelian group. It has rank, and this is the so-called Picard number. And then we have the following estimate. Then we have that the rho. So this is called the Igusa-Artin-Maser inequality. So this is the second Betti number, so this is 22. Provided that the height is of course 1. So then the rank of the Néron-Severi group is bounded by something which is related to the height. And so from this, what are the possible values? Well, it can be infinite, but we know that the rank of the Picard, sort of the second Betti number of a K3 surface is 22. I mean, I haven't explained this, believe me. It's an algebraic, it's a projective surface, so the rank of the Néron-Severi group is at least 1 because there is an ample line bundle, and this tells you that the height can take only values between 1 and 10. So the interesting question is, what can we say about the rank of the Nernst-Severi in case the height is infinite? Now, we have that. What people conjectured was that if the rank of the Nernst-Severi is 22, a value that cannot happen in characteristic 0. For those who know about this, there is a Chern map sort of in characteristic 0 which goes to H1, omega 1, or H11, which for a K3 surface is 20-dimensional. So this tells you that the rank of the Nernst-Severi group can be at most 20 in characteristic 0. However, in characteristic P, it's possible that this value goes up to 22. And if this happens, then you can show that the height has to be infinite, because otherwise you have, so I mean, if it was finite, then it would simply contradict this formula. So this implication is easy, well, once you believe this formula. And in fact, if P is odd, so not, I mean, characteristic 2 is something people cannot do. This is the so-called take conjecture. So people believe it to be true in any characteristic, but by recent work of Morlik, François Charles, and then Madapuzzi-Pera, we know that in fact these two are equivalent. So the height of the formal Brauer group being infinite, being equivalent to saying that the formal Brauer group in fact is the formal additive group law, is equivalent, says something about the rank of the Nernst-Severi group on a K3 surface. And so let me at least, for those people who have been bored until now, let me at least give a little bit of what's going on and what is happening here. Maybe I should have this on the blackboard. Now I'm using fancy stuff, but sort of sketch. But I want to kind of show how these things come from. Associated to we have this formal Brauer group, which is a one-dimensional formal group law. We have its Cartier-Dieudonné module. We have seen this before. Now I'm curious. So, if you want to classify formal group laws, commutative formal group laws that are more than one-dimensional, I mean, the height is not sufficient. So what do? There is an infinite dimensional formal group law lurking around, which is the formal Witt group law. So you may have seen these Witt polynomials, x naught to the p plus p and so forth. This is a sequence of polynomials, and you can cook up an infinite dimensional formal group law from that. And then you can look at homomorphisms from this universal formal group law to so this universal Witt group law to a given formal group law commutative, so commutative one. And this set of homomorphisms comes with some structure. It's a module over the Witt ring, and it carries, because the Witt vectors have this, carries some, Frobenius, Verschiebung, you get some extra structure. So associated to a formal group law, to a commutative formal group law, you get a module over the Witt ring plus some extra structure. This is the Cartier-Dieudonné module. If height of the formal Brauer group is finite, then, so this is nothing about the formal Brauer group, this is actually something about formal group laws in general. So if you have finite height, then this is a free WK module. This is the Witt ring. Of rank H, where H is the height. So, and it turns out that if the height is finite, then this here identifies itself with a second bit vector cohomology. So I can take values of H2 not only in OX, but I can witify it. So now I can kind of look at the bit vector. And this has a map to second crystalline cohomology. So this is the cohomology that you should actually study if you work with
H2 of what?
WOX.
W?
It's like the bit ring, which is defined by these polynomials, but the bit construction can be done for every ring. In particular, you can do it for every sheaf of rings. And so in particular, you can do WOX. And this is what Serre started this in his Mexico paper from the 1950s. And he realized that sometimes he runs into trouble. For example, this bit vector cohomology may not be a finitely generated W module, because it's an inverse limit over something. Actually, we know precisely when it is the case, because this isomorphism holds also the height is infinite. The Cartier-Dieudonné module of GA, for example, is just a formal power series ring in one variable over the ground field, which as a module over the Rit ring is not finitely generated. Therefore, this one is not. So it's something which can be nicely explained using this framework. I think that was not clear in the 50s. So this is why people kind of disregarded it. And you should think of, and this can be made precise, H2 Chris should be built up from H2WOX, H1W omega 1, and H0 of W omega 2. So you should witify, so to speak, all these notions, and then you should get something like a Hodge decomposition for crystalline cohomology in terms of something else. This something else is called the Ulysses-de-Rham-Witt complex, and it's unfortunately not so easy to define, and even worse, it's not true. I mean, it's, you know, you have to be very careful. There are some natural maps which fail to be isomorphisms precisely if these heights, for example, are not finite. Nevertheless, as I said, this is just a sketch and a little bit of propaganda for things to come. The formal Brauer group gives rise to some structure inside this crystalline cohomology group, and it gives rise now to a rank H submodule where the Frobenius acts with slope. I'm not saying what this is, because I get it wrong myself. Anyway. In any case, you also have a crystal
H submodule where?
inside this crystalline cohomology group via this map. So you have to show that this is in fact injective. I'm skipping a couple of things. I just want to motivate what is going on here. What is going on is that the formal Brauer group contributes a term inside this cohomology group. And you also have a crystalline Chern map, a map from the Néron-Severi inside this. And the image inside here will be of Frobenius slope 1. So the larger the formal Brauer group eats up rank H. By Poincaré duality, it actually eats up rank H 2 times H, because there is one part of this slope, and then there is some other slope, which is 1 plus 1 over H. So this tells you that since the image of the Néron-Severi map has Frobenius slope 1, and the formal Brauer group, if of finite height, eats up rank 2H, the rank of the Néron-Severi can be at most this. So this is where this inequality comes from. It's actually not such a miracle. It basically says that the image of the larger the formal Brauer group, the larger the height of the formal Brauer group, the larger there is this Frobenius subcrystal inside crystalline cohomology, such that there's less space for the rank of the Néron-Severi. Unless something interesting happens. Namely, if the height is infinite, then the contribution here is sort of what's coming from here is 0. And it turns out that this is purely of slope 1. And so it could be that the rank of the Néron-Severi is actually 22. And this would follow from the Tate conjecture. For those who haven't seen, the Tate conjecture is a sort of arithmetic version of the Hodge conjecture in the 1-1 case. You know, people in arithmetic can always do less than people in geometry, because things in arithmetic are harder. So there is a kind of version of this thing of characterizing 1-1 classes inside crystalline cohomology. It's the so-called Tate module. And the Tate module in the case of infinite height would be of rank 22, suggesting that the K3 surface, at least in the K3 case, we can say something, where the height of the formal Brauer group is infinite. That's equivalent to saying that crystalline cohomology is purely of slope 1, and that should be equivalent to PK rank 22. As I said, solved last 2 years, at least for K3 surfaces. In general, it's still wide open. And so let me now come to a conjecture relating all this, and I will prove this conjecture tomorrow. Yeah, so this gives you this estimate. This gives you this, which is just a straightforward application. And why the Tate conjecture is true, this would be more of a talk of itself. So what I want to say now, finally, with Artin. Conjecture. So we have for a K3 surface, how much time do I have now?
Like
10 minutes.
It's just not much I have to say. And we have the following theory. So let X be a smooth and projective surface. So I have another bracket closed field. B2. The second Betti number. So this is, for example, the second L-adic Betti number with L prime to B, or second rank of the second crystalline cohomology. And then we have a result of Iguza, which says that the rank of the Neon-Severi is at most the rank of the second Betti number. In characteristic 0, we have the stronger inequality, rho is at most H11. But the problem is, in characteristic P, you can write down a cycle map. You can write down this map, it's called D-log or something, which goes from pic to H11. But what's the reason? Why is it injective in characteristic 0? It's injective because you have an intersection pairing on both sides, which is non-degenerate on both sides. Therefore, it must be injective. But the problem is in characteristic P, it's still, the intersection pairing on the pic is still non-degenerate. But one side is an abelian group, it's a Z to the something, and the other side is a vector space of characteristic P. So suppose, just for a second, the intersection pairing on Neron-Severi would be non-degenerate in something like this. Surely non-degenerate in characteristic 0, right? But if you reduce it mod P, it becomes 0. So that's the reason why the cycle map to H11 may fail to be injective. However, if you believe, of course, Iguza didn't know that at his time, that there is an injective Chern map to crystalline cohomology or to étale cohomology, we totally believe that the rank should be bounded above by B2. That's one. And then we have the following result, Kikuchi-Oda, which says that if X is uni-ruled or unirational, because this is what I was interested in, then we have that rho is actually equal to B2. And so if X is a K3 surface in characteristic P, what do we have? Well, X could be unirational. Which would imply that the PK rank is equal to B2, which is actually 22, which would imply that the height of the formal Brauer group is infinite. Now, let's say P bigger or equal to 3. Then we have that also this is okay for the take conjecture, which, as I said, you might think of as a kind of Hodge-type conjecture for 1-1 classes. Now, for people especially working in complex geometry, the question is, why can it happen that a K-free surface all of a sudden has so many cycles? And the easiest way to explain the success of cycles, why is every class algebraic, would be that it is unirational. So the conjecture was, by these people here, a K-free surface is unirational if and only if the pK rank is 22. And so, let me give the evidence that we had until last year. So the evidence until 2013 was it's okay if the characteristic is 2 and rho is equal to 22. It's okay. I'm not introducing this at the moment. I'm just saying it says that there is a 5-dimensional family where it's true. So these two results are due to Lüroth and Shafarevich. This is how they come into it. It's okay if P is 5 and sigma naught is whatever it is. That means at most 3. It says that there is a 2-dimensional family. So supersingular, these are called supersingular. K-frees form a 9-dimensional family. So it's okay for a 9-dimensional family here. It's okay for a 5-dimensional family here. A 2-dimensional family here. So this is done in the early 2000s by Fu and Shimada. And it's okay if P is bigger or equal to 3 and X is a Kummer surface. A is supersingular. So that is due to Shioda. So here supersingular means that, for example, for an abelian surface, this means that you look at the p-torsion points and that the p-torsion subgroup scheme is infinitesimal. So on the level of k-rational points, you will never find another p-torsion point other than the 0. So, because, I should say, how do you prove these things? Lüroth and Shafarevich came up with a structure called quasi-elliptic fibrations. But the problem is these kind of structures only exist in characteristic 2 and 3. Fu and Shimada used another trick that does not generalize to higher dimensions. And this one is ingenious. Shioda simply, he writes down a projective model for the surface. And then, he goes to the function field and he simply writes down a unirational parametrization. He says that the function field of such a surface then is contained in some purely transcendental extension. And so, I don't understand how you write down the polynomials he did. I once asked him, and he said, I said, like, how did you find that? And he said, well, by just being very patient. So, so all I'm saying is, I don't really understand this proof. It has been checked several times, but it's, it's simply by writing down. And so tomorrow I will explain why this conjecture is true in general. And I stop here for today. Thank you. Comments?
Thank you very much.
It's